This webcast looks at Worksheet 1C, where we're doing some practice with dimensional analysis. And so let's look at the first question here, where we've got a formula for finding the volume of a cylinder. And we want to confirm that this is a valid equation, if you will. And so we're going to do dimensional analysis, and the first step is to replace each of these variables with its dimension. Now, in the wording of this problem, it's giving me the dimensions. It says volume is known to have the dimension of L cubed. So on the left-hand side, the dimension of volume is length cubed. Oh, I get to something. Here's a pi. Is pi a physical characteristic? No. Pi is a numerical constant. So we're going to ignore it. Or at least ignore it for this purpose, right? For doing the dimensional analysis. Okay. So I keep going. My next variable is r squared. Well, it says radius and height both have the dimension of L. So the dimension of r is L, and that variable r is squared in this equation, so I'm going to square it here. Then the dimension of h, the variable for height, is also L. And so I'm looking to see, is what's on the left, does that have the same dimension as what's on the right? And in this case, it does, right? L squared times L is L cubed. So I'm going to say yes. This equation is likely to be valid. I'm saying likely because using dimensional analysis has not confirmed that pi was the correct numerical constant. But I do know that the volume is proportional to radius squared times height because the dimensions work out. Let's look at another example. Let's look at number 2. Now number 2, they're giving us 4 different equations, and we're trying to find which ones are dimensionally valid. And up above here, they're giving me a table, and each variable is listed, and next to it, it's showing its dimension. Notice that this table is in 2 parts, right? There's the left-hand part and then there's the right-hand part. But I can find the dimension for each of these 6 variables because at this point in our class, we're not expecting you to know that the dimension of force is mass times length over time squared, and so on. Okay, let's look at B. For the sake of time, I'm going to skip A. But here we have an equation that says v squared equals 2 times a times x. And so I want to look in this table, and for each one of these variables, I'm going to substitute in the dimension of that variable. V, I see in the table, is velocity, and it has a dimension of L over t. So I've got L over t. That's the dimension of v, but in this equation, that variable is squared, so I'm going to square that dimension. Now, here I've got a number, 2, and I ignore numbers because they don't have a physical dimension. Okay, so I just ignore the 2. A, in the table, I can see that A, or acceleration, has a dimension of L over t squared. And then I have x. X has the dimension of L. So now I want to use just the normal rules of algebra to simplify both sides of this equation to see if they have the same dimension or not. Okay, on the left-hand side I have L over t squared. When I distribute that exponent, I get L squared over t squared. And on the right-hand side, I have L over t squared times L. That also gives me L squared over t squared. So this is a valid equation. Let's look at C. So here I have velocity equals acceleration times time squared. So let's see. For velocity, I plug in the dimension, which is L over t. The acceleration, I see, has a dimension of L over t squared. And then I have time squared, and the dimension of time is t, and that variable is squared, so I square the dimension as well. Now I start simplifying, just using the normal rules of algebra. On the right-hand side, there's a t squared in the numerator and a t squared in the denominator, and so those can cancel, and I end up with L over t on the left, but I end up with L on the right. So this is not a valid equation. There's no way that can be valid because there's a different dimension on the left than on the right. I'd like to go down and look at number 4, because in number 4 we're using dimensional analysis in a different way. Here we are trying to find the dimension of the spring constant. So this is a physical constant that we are trying to find. By the way, there's a little typo there. Okay. And so they give me the equation right here. I'm going to write the equation. F equals negative kx, and the spring constant is k. So I'm going to solve for that spring constant. So k would be negative f over x. By the way, what is this negative? That's negative 1, right? Negative 1 is a numerical constant. And will be ignored for our purposes of dimensional analysis. Okay? Okay. So let's do the dimensional, find the dimension of k. So this is Hooke's law. That means this is a law of physics. This is a valid equation. It's been demonstrated, and there's a lot of evidence to support it. So I'm going to trust this equation, and since it's valid, it must be the case that the dimension on the left equals the dimension on the right. So the dimension of k, which is on the left-hand side of the equation, must equal the dimension of this stuff on the right. So I'm doing dimensional analysis here, so I'm going to ignore that negative sign, that negative 1. But the dimension of the force, F, is this ml over t squared. I'm reading that from the table above. And the dimension of x is L. And so now I can simplify. I have one L in the numerator and one L in the denominator, so they can cancel, and I end up with a dimension of mass over time squared, and that must be the dimension of that spring constant k.